course, our screen share has to be the whiteboard. That's all we got. I don't have a PDF of the book like I do with the other ones. So let me move things around. If I can get it to, you can't see this, I don't think, but my the toolbar, taskbar for Zoom gets right in the whiteboard space, and it's done by Zoom, so you would think they wouldn't do that. And then the taskbar for the whiteboard is right in the white space, and you would think they wouldn't do that either. And then you and I are over here just in a little bit in the whiteboard space, so I scooted us over some, and then I take my whiteboard and move it as far to the left and up as I can, so I get the maximum amount of white space to write on. Okay. Well, still the Y chromosomes are sleeping in today, I guess. Okay. Where we left off last time, we're in Chapter 2, Matrices, Section 2.1 still. Hopefully we'll get through it soon, but this is a long section. And we were talking about, in general, how do you multiply matrices? And this next one, since some of them don't have a book or can't be watching the book while I'm in class, I just did not think there was room to write this one. So here's what we're going to do. I'm going to write out this big, long, hairy matrix multiplication problem here. Okay. We're going to multiply matrix A, whose elements are A11, A12, A13, dot, 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 up to A1, I believe they name it N. Yes, they do. And second row would be A21. Is someone trying to come in? Let me see. Well, I can't find my cursor. Oh, I know why, because if I'm holding the pen too close to the Wacom board, it won't let my cursor move. Nope, it's still just the two of us. So, all right, A21, A22, A23, and then we'll do a dot, 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 and get out to A2N. And the next one would be, of course, A31, A32. I keep hearing noises. I don't know what that means. Yep, still just the two of us. A33, dot, 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 out to A3 sub n. And then we'll just dot, dot, dot this on down to go up to A sub M1, A sub M2, A sub M3, and dot, dot, dot that over to A sub Mn. So all these are dot, dot, dots. That's a dot, 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 and everywhere a dot, dot, dot. All over the place, dot, dot, dot. Okay, you get the general idea. So matrix A is M rows, you can tell that here, by N columns. You can tell that here. Now we're going to multiply that by some matrix B. B will be B11, B12, B13, dot, 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 until you get to B1. Now, it could be an N, but it doesn't have to be. So I'm going to keep it generic here and make this a P. I think that's what the book uses. I'm going to check and see. Yes, it is. Okay. And then the next row would be B21. If I write too fast, it doesn't write. B22, B23, dot, dot dot B2P. Ah, here comes James. Let me get James here. So half the Y chromosomes are showing up anyway. James is here. And we're hoping still that Jesus will make it in. I am recording, so in case they don't, he doesn't, he can hear everything. James, you're here. We're doing the top of page 44. We're in Chapter 2, Matrices 2.1, Operations with Matrices, and we're doing the generic case for matrix multiplication. And I've just given you matrix A, which is an M by N matrix, M rows, N columns. And now I'm doing matrix B, which so far we see has P columns. We haven't gotten to the rows yet, but we'll get there. B sub 3, 1, B sub 3, 2, B sub 3, 3, and we'll dot, dot, dot until we get out to B sub 3P, and then we'll dot on down there until we get to B. Now, here's what B has to have. It has to have N rows because A had N columns. And the only way to do your multiplication, the number of columns of the first one has to equal the number of rows of the second one. So this will dot, dot, dot on down to B sub N2, and this dot, dot, dots down to B sub N3, and this dot, dot, dots over to B sub NP, and this dots on down to that too, and everything in the world dots to everything. Okay. Now, so B, the matrix B has to be, if I could find my pen, there it is, B has to be an N by P. Whatever M is, it doesn't matter. Whatever P is, that doesn't matter, but the N's have to be the same. So you can basically wipe out this and wipe out that, and your quotient matrix, the result of that, I'm going to write it down here. It is going to be some C, C11, C12, C13, dot, 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 out to C. Now, 1, we know that is. What is it going to be? That's also going to be P, because the number of columns for it is what this is. The number of rows is what was left there. So this will go down to C21, C22, C23, dot, dot, dot to C2P. This will be C31, C32, C33, dot, dot, dot over to C sub 3P. And then this dot's on down to, and this has to wind up with C sub M1. Dot, dot, dot down to C sub M2. This dot, dot, dots down to C sub M3. And this dot, dot, dots and dot, dot, dots down to C sub MP. And dot, 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 everywhere dot, dot. Okay. Now, so the quotient matrix C has got to be an M by P. These two, the number of columns of A must equal the number of rows of B, otherwise you can't multiply. Can't. And if they are, the product matrix will be the number of rows of the first one and the number of columns of the last one. Okay? So that's basically summarizes that. Now here's how they write it in sort of their shorthand, that the A sub ij plus, no, I'm sorry, I think that's a 1. I can't read. They have such fine print, they put it in this. No, okay, I got what they're saying now. A sub I1, if I can get my pen back here, let me go on and erase. Okay. It's the product AI1 B1J plus AI2 B2J plus AI3 B3J plus dot 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 up until you get to AIN BNJ, and that's equal to your CIJ. Okay, now that's exactly what we were doing. I wish I had 2 markers I could do. I can only show 1. What we're doing here is multiplying the, whoa, where did that come from? To get to this first element here, which is the first row, first column, you take the first row of A, that's your A1 whatevers, okay, your AI whatevers, letting them increase, and do it times the first column, which I can't get my pen to show up, there it is, of B. So you go across A while you're going down B, and that's why the N that's here has the equal to N that's there, because you have to have the same number of entries to multiply, and that gives you your C11. To get your C12, you do the first row of A by the second column of B, and so on and so on, to get to the say right in here, the ith element, the ij element in C, you go down to the ith row, let's put it here, ij element here, somewhere down in here. You go down to the ith row here, and the jth column here, you go to the ith row here, and the jth column here, and you do those down there until you get that. So that's how you get it. I don't know if that makes it any clearer, but the book made a big deal about it. To me, it was a lot of writing. Okay. Now, they do have a discovery. So let's do the discovery. Any questions on this before I erase the screen? Okay, I'm going to clear the screen here. Just make sure that, yep, Jesus still hasn't shown up. Here's the discovery. Let A equal, goodness gracious, it's writing, sometimes it won't write at all, other times it writes just wherever it wants to without me doing a thing. This is 1, 2, 3, 4. Now it's writing better. Well, I say that right before it quit writing better. And B is equal to 0, 1, 1, 2. Okay. Now, the question is matrix addition commutative? Which means, is A plus B equal to B plus A? That's the question. Well, let's do the A plus B here. To add matrices, you just add the corresponding elements. So this would be 1 plus 0 is 1, 2 plus 1 is 3, 3 plus 1 is 4, and 4 plus 2 is 6. Okay? All right. Is that equal to, and let's do B plus A. 0 plus 1 is 1. 1 plus 2 is 3. 1 plus 3 is 4. And 2 plus 4 is 6. It sure seems like it is. Yes, matrix addition is commutative. It doesn't matter which order you add, because you're adding element to element, corresponding elements, and they are real numbers, and real numbers are commutative when you add. Okay? Now, the second question is AB equal to BA? So in other words, is the product of AB, is that equal to the product of BA? Now, time out for a moment here. The only way you could even do this is that A and B would both have to be square matrices, because if one of them was not square, say A was a 2 by 3 and B was a 2 by 2, you can't multiply those because the inner things are different. Now if A was a 2 by 2 and B was a 2 by 3, yes, you can do that. Your answer is going to be a 2 by 3. But if your B was a 2 by 3 and your A was a 2 by 2, which I just said, you can't multiply BA. So the only way you can even do this operation is for these both to be square matrices, same size square matrices. Okay? Then at least you can multiply. But the question is, when they are, like these are, do you get the same product? Well, let's see what we get for AB. AB, this is a 2 by 2, that's a 2 by 2, so this is going to be a 2 by 2. Okay? 1, 2, 1, 2. Okay? Now, this element right here, if I can get my pen to show up, where did it go? There it is. Okay. This element right here, first row, first column. So let's do that. First row here by first column here. 1 times 1 is 1, plus 3 times 4 is 12. 1 plus 12 is 13. Agreed or not? Okay. This, where is it? There it is. This element here is the first row's second column. So we'll still be with the first row, but now do the second column here. 1 times 3 is 3, plus 3 times 6 is 18. That would be a 21. Okay. This element here is the 1 element here. So we take the second row of A times the first column of B, and that would be 4 plus 24 is 28. Okay. Sorry. I'm losing my voice again. The 2, 2 element here, second row, second column, that's 4 times 3 is 12, plus 36 is 48. All right. Now the question is that equal to BA? In order to do BA, I'm going to put A on this side, and that's no, A on. What was I doing? Y'all let me do that. Oh my goodness, I'm going to fire you, okay? I was doing the wrong thing. I can't believe y'all let me get away with that, okay? I was looking at the wrong ones. Here is A and B up here. I was doing these two here. The 1-1 entry here, this is embarrassing. 1-1 entry here, first row here by first column there. I thought those numbers were awfully large. That'd be a 1 times 0 is 0 plus 2. That's going to be a 2. Okay? Then first row here by second column here. That'll give you the 1, 2 entry here. That'd be 1 times 1 is 1 plus 4 is 5. I'm going to have to drink something for my throat. Sorry. Sorry about that. Okay. There it is. Sorry. The 2-1 entry here will be second row here by first column there. 3 times 0 is 0 plus 4 is 4. And the 2-2 entry down here, whenever I can find my key, there it is. 2-2 entry here, second row here, second column there. 3 times 1 is 3 plus 8 is 11. Alright, now this is where I ran and found my error before. Let's do B times A. Well, to do that, I'm going to repeat A over here so I get it in the right place. That's a 1, 2, 3, 4. Very creative here. And this one, of course, is going to be a 2 by 2. So it's going to be 1, 2, 3, and 4. The 1-1 entry here, BA, will be the first row of B times the first column of A. That would be a 0 times 1 is 0 plus 1 times 3. That's a 3. Alright, already you know, nope, this is not going to work, but let's carry it on out. The second entry is a 1, 2 entry here. So first row here, second column there would be a 0 plus 4 is 4. Nope, not going to work. And then the 2, 1 entry here, second row here, first column there, 1 plus 6 is 7. No way. And then the 2, 2 entry here, second row here, times first column there, 1 plus, no, second times second. 2 plus 8 is 10. Nothing in the world matches here. No. Multiplication is not commutative. Definitely not commutative. Okay. So that was discovery, middle of page 44. Let's do example 5. All right, to clear? Any questions? All right. So let's do the matrix multiplication here. And this one, you can go to larsonlinearalgebra.com for an interactive version of this type of an example. All right. So we're going to try to do some multiplying here. So the first matrix they have here is 1, 0, 3, 2, negative 1, negative 2, and we're going to multiply that by negative 2, 4, 2, one, 0, 0, negative 1, 1, negative 1. At least I think that's it. All right, yeah. That's the A one. Let's sorry folks, let's see if plain water will help. This was, well, y'all were in class I think yesterday afternoon when this was the same thing. I just got so dry in the throat I couldn't handle it. All right, first thing we do, can we even do this? What size is A here, the first one? What size is that? 2 by 3. What size is this one? 3 by 3. The answer is yes, you can do it. These two are the same. I struck them out so I could know what the product matrix was. It has to be a 2 by 3. When you wipe out the two that are the same, then what's left is what your answer is. So this is going to be a 2 by 3 as well. 3 columns, 2 rows. This first entry here is the 1-1 entry. So you take the first row of the first matrix times the first column of the second matrix. So I just heard a ding. I don't know. Nope, we still got just the 2 students here. So I don't know where Jesus is. All right, so let's do it. First row by first column. 1 times -2 is -2 plus 0. I can do that one. That's -2 minus 3. So that's going to give us a -5. Agreed? It's a pretty ugly 5. Okay, the second entry here is the 1-2 entry. So we'll take still the first row here, if I could get my pen to show up somewhere, first row here by the second column here. And that gives us a 4 plus 0 plus 3. I think that comes up being a 7. Okay, this entry right here is the 1-3 entry, so that means we'll stay with the first row here and do the second column here. Okay, so that's going to be a 2, third column here. 2 minus 3 will be a -1. That's a pretty ugly minus sign. I'm sorry folks, I've got to have something. My head is feeling awful. I think maybe today is a little bit of hunger because it's been a long time since breakfast. Okay, and let's see, we go until 12:45, right? Yeah, okay, so it's going to be a while. 45 minutes to go here. Okay, so that's a -1. Still, I'm losing my voice. This entry here, the next one here, is the 2-1 entry, second row, first column. So we'll do second row here times the first column there. 2 times a -2 is -4. -1 times 1 is -1, so that'd be a -5. Plus 2 would be a -3. All right. The 2-2 entry here, second row here, second column here, would be an 8, 0, -2, so that would be a 6. 8 minus 2 is 6. The 2-3 entry here, second row here, third column here, is going to be 4 plus 0 plus 2. 4 plus 2 is 6 again. All right, let's see what they got. -5, 7 minus 1, -3, 6, 6. Good for them. Okay, let's see if we can squeeze B on the same page. Here we have 3, 4, negative 2, 5. And they're going to try to multiply that by 1, 0, 0, 1. First question is, can you even multiply them? Well, what are their sizes? 2 by 2, 2 rows, 2 columns. This is a 2 by 2, 2 rows, 2 columns. And certainly since these two numbers are the same, wipe them out and that gives you a 2 by 2. So yes, you can multiply these two. It will produce a 2 by 2 matrix. Now, goodness gracious, I've seldom felt so lightheaded. I feel like I could just lay down and fall asleep, but I'm going to try not to. All right, first entry here, entry here, the 1, 1 entry. We take the first row of this one by the first column of that one. That's 3 times 1 is 3, plus 4 times 0, that's 0, so that just gives us a 3. The 1, 2 entry here, first row again, by the second column here, 3 times 0 is 0, plus 4 times 1 is 4. Okay, the 2, 1 entry here, second row here, by first column here, that would be a negative 2 times 1 is negative 2. Plus 5 times 0, that would just simply be a negative 2. Oh man, the 2, 2 entry here, second row by second column here, and that would be negative 2 times 0 is 0, plus 5. Okay, I know that's lousy writing, but man, I'm just barely hanging in here. I have not felt this bad in a while. Okay. Now, what I want you to notice here is your first entry here, this first matrix here, is exactly this matrix here. Identically the same. Identically the same. Which means we can call this matrix here, and that is a fairly strange looking little matrix there, we can call this the identity matrix. Now this is the identity matrix of order 2. Let me tell you a couple of things about identity matrices. They're always square, never rectangular, square, okay? And I'm jumping the gun on this, but the diagonal elements, the main diagonal elements are always 1s, and every other element is a 0. Now this is only a 2 by 2, so there's only 2 elements on the main diagonal and 2 that are not on it. So the 2 on the main diagonal are 1, the other 2 are 0. If you had a 3 by 3, which has to be square, only the main diagonals are 1s and everything else are 0s, above and below that main diagonal. And sure enough, when you multiply a matrix by an identity matrix, you get the first matrix you had. Okay? Now, it acts like the number 1 in regular multiplication. Multiply any number in the world. Negative pi thirds times 1 is still negative pi thirds. So 1 is the multiplicative identity element of the real numbers. Okay? Well, the identity matrix, the appropriate size identity matrix, is your multiplicative identity in matrix multiplication. Now, let's see if we can squeeze number C in underneath here. C is a 1, 2. That's weird looking 1. 1, 1 times negative 1, 2, 1, negative 1, and we ask ourselves, can you even multiply that? 1 is so ugly. The pen just decided to start writing before I even got to where I was on the screen. So let me get that 1 to be there. Okay. Now, this is a 2 by 2. This is also a 2 by 2. And because these two entries are the same, our product matrix is going to be a 2 by 2. Okay, so that means you have 2 rows, 2 columns, 2 rows. Okay, for the 1, 1 entry here, you take the first row here, first column there. 1 times negative 1 is negative 1, plus 2 is 1. 1, 2 entry here, first row, second column, is first row here times second column here, and that would be 1 times 2 is 2, plus a 2 times negative 1, that would be a 0. 2 minus 2 is 0, if I can get my pen to show up. Okay, my internet connection is unstable, it says. My internet says I have 4 bars, so I don't think it's unstable. I think somewhere out there in ether space somewhere something is unstable. Did I break up a little bit when that was doing? I quit doing linear algebra and just started talking. Could you tell? Still can't believe Jesus has it shown. And he's not. Okay. All right. The 2, 1 entry here is second row here by first column here. That would be a 1 times minus 1 is minus 1, plus 1 times 1 is 1. Minus 1 plus 1, sure enough, is 0. Okay? And then finally the 2, 2 entry here, second row here by second column here, that would be 2, 1 times 2 is 2, plus a 1 times minus 1 is minus 1, 2 minus 1 is 1, and look at what we got. We wound up with an identity matrix, an I2 identity matrix, which is rather bizarre. And what that tells us, way jumping ahead, is that these two matrices here, number one, they've got to be square, I think, yeah. These two matrices here have to be what they call inverses of each other. Just like multiplying 1, let's do 1/9 times 9 over 1, that gives you the number 1, okay? Or 7/15 times 15 over 7, that gives you the number 1. Those are multiplicative inverses of each other. Now we have matrix inverses. Okay. Now, it's a bit bizarre because, frankly, they don't look like they're inverses of each other, but they have to be. All right. Now, let's move on. I think I'm going to have to clear the screen here. Anyone need that up a little longer? Okay. Here is D. D is this matrix. It's called a row matrix or row vector. 1, -2, -3. That line up there means absolutely nothing. It's just where my pen touched the page and whereas sometimes I can't get it to write, this wrote big time. All right, multiplying that by 2, -1, 1. And by the way, this is what they call a column matrix or a column vector. Sorry, I'm having trouble talking. So what is your dimension of this one? What's the size? Can we even multiply these? What size is this one? 1 row by 3 columns. What is this one? 3 rows by 1 column. And sure enough, the 3's are the same. The 3's basically go away, and you're left with a single 1 by 1. You get one answer. Okay? Now, I'm sorry, I'm going to have to get another swig of something here. My wife, when I told her what happened yesterday, she said, sounds like you got dehydrated. And maybe that was it. I don't know. For some reason I went to draw mode. I didn't want to. So this is going to be a 1 by 1, meaning just a single number here, which you don't usually think of as a matrix, but in this case it is. So let's do it. The 1 1 entry here is a 1 1 entry, so you'll do first column here by a first row here by first column there. 1 times 2 is 2, plus a -2 times -1 is +2, so that'll be 4, plus a -3 times 1 is -3, so 4 minus 3 is 1. Now guess what? That just happens also to be a 1 by 1 identity matrix, but that's these are obviously not inverses of each other because inverses have to be square, and these are not. Okay, let's do the D then. I mean the E. The E kind of reverses things here. That starts with a 3 by 1 matrix, 2 minus 1, 1, and multiplies that by the same 1 by 3 matrix, 1, 1, -2, -3. Okay, now it almost looks like we're trying to see if they commute. You definitely will see they do not. What do we have here? What size is this? 3 by 1. This one's a 1 by 3. The inner two numbers are the same, so they will multiply, but this gives you a 3 by 3 matrix here. Okay, if drinking doesn't solve this, let me see if eating a little protein might. I have an almond up here. Sorry about chewing in class. This is probably going to be loud. So this turns out being a 3 by 3 matrix because that's what's left. I didn't write it down. 3 by 3. How do you get that? First row, first column here. 1, 1, first row, first column. First row, 2, first column, 1. That's going to be a 2. 1, 2 entry here. First row again. By second column here, that's a -4. 1, 3 entry here, first row here, third column here, -6. Sorry, this Wacom tablet is really small, I'm left-handed, which means I write like this, and my knuckles keep hitting this top row of buttons here. I have no idea what the buttons are. I know the first one's basically almost like an erase button. It erases the last mark I made. The second one's a precision button, which I have no idea what it is, but it won't do a thing until I press it again to get it to go off. I'm going to eat another almond. Okay, let's go to the 2-1 entry here. Second row, first column. Second row here is a -1. First column here is a +1. That will be a -1. The 2-2 entry here, second row here, second column here, that's going to be a +2. 2-3 entry here, second row here, third column here, a +3. Okay, 3-1 entry here, third row here, first column here, that's a 1. 3-2 entry here, third row, second column, that's a -2. And the 3-3 entry here is third row, third column, that's a -3. If I could find my, there it is, -3. Okay, let's make sure that we did the same thing they did. 2, -4, -6, -1, 2, 3, 1, -2, -3. Got it. Okay. Sorry. Now, you might ask yourself, why are we doing this? And that might be a very legitimate thing. But remember, one of the functions, one of the applications, one thing that matrices are used for is solving linear equations. Now, we've done that. We've done it a couple of different ways. Excuse me. Okay, we've done it with Gaussian elimination, and we've done it in Gauss-Jordan elimination. Well, now we're going to do it with matrix operations. And this is going to start sort of going to take us a while to get where we need to go. So let's get started on it now. Here is your typical system of equations. 3 equations, 3 unknown. Coefficient a11 times x sub 1, 1, plus a12 times x sub 2, plus a13 times x sub 3, okay, and that's equal to some constant we'll just call B1. Okay. Second equation will be a21 times that same first variable, x of 1, plus a22 times its x of 2, plus a23 times x sub 3, and that's equal to B2. I thought I heard my phone buzzing. Maybe it's my head buzzing. I'm sorry. Alright, here comes, he's Miguel today, okay? Jesus is coming in. I can't get him admitted. There we go. Alright, way to go. Perfect attendance again today. Just barely, but you got here. Okay. Okay. Lost my pen. equation in the system of equations, as normal, if I can get my pen to come back, a sub 3, 1, x sub 1, plus a sub 3, 2, x sub 2, plus a sub 3, 3, x sub 3 is equal to b3. Just a very, look at that. Why it does that. Okay. Now, that's a system of three equations, three unknowns. Now, okay, we can also write that this way. We can write it as a coefficient matrix, and we've done this before, but not quite this way, because we didn't do multiplication at the time. Coefficient matrix is A11, A12, A13, just the coefficient matrix, not augmented. A21, A22, A23, A31, A32, and A33. Okay, now we're going to multiply that by, now that we know how to multiply, by a column matrix or column vector is just x1, x2, and x3. Now this doesn't look like what we've done before, and then that's equal to another column vector, b1, b2, and b3. Now, that's the claim. Let's see if it's right. Well, this is a 3 by 3 matrix. Okay, this is a 3 by 1 matrix. And sure enough, since these two are the same, it should result in a 3 by 1 matrix. And it does. Okay, so at least the sizes are right. Let's see if the elements are right. For this first element here, which is the 1, 1 element, we would do first row here by first column here. That would be A11 x1 plus A12 x2 plus A13 x3 equal B1. That's exactly what our first equation is. And if we did the 2, 1 element here, that would be A sub 2, 1 x1 plus a sub 2, 2x2 plus a sub 2, 3x3 is equal to b2. That's exactly what their second equation is. And similarly the third. So yes, this is another way to write that system of equations in as a matrix product problem, because these are exactly the same representation. Now, we haven't said how this is going to help us solve it, but we've noted this is how you can write that. Okay? Now, what we say then, we give this a name. This, our coefficient matrix, we'll call matrix A. And we'll multiply that by, remember I called this a vector? That would be vector X. And that's equal to vector B. So another way to express this is AX equal B. And that's exactly what we've got there. Okay? Where X and B, because they are vectors, I put the vector symbol over them. They're also column matrices, which is fine, but they're still, that's also a vector. All right. Let me clear this out of the way. If I can make it through this next 20 minutes or so, it's going to be amazing. Okay. Here is example 6. It says solve this matrix AX is equal to 0. Now this is something a little new here. I think we touched on it before, but we're coming back to it now. Most of the time, matrices are expressed as capital letters, unless they happen also to be vectors, and then we put them lower letters, and the book does them in bold. I do them with I'm sorry, I moved my microphone. Were y'all able to hear me then? Because I had my microphone up. Were you still able to hear? Or was anyone listening? Well, I can't get a response. Now, I'm afraid that won't record very well either, so hopefully I haven't messed up too badly, but I had moved my microphone up either to chew on the album or sneeze or something like that. I forgot to put it back down. Okay? It says solve that matrix where the A matrix here is this one. One, negative 2, 1, 2, 3, negative 2, the X matrix here, X vector here, is the column vector, X1, X2, X3, big surprise there. And of course the zero vector, and this is what I was saying before, got off on it. The zero vector is the vector of whatever the appropriate size of it needs to be, but every element is 0. And what I was going to say is we usually represent matrices by capital letters. We've been doing that. But here's a matrix, but it's also a column vector, so we write it as a lowercase letter. The book writes it bold. I can't write bold, so I put the arrow symbol over it. But here's the one that's a little bizarre. The zero vector we write as the number 0, not some letter, but the number 0. It's the only one we do this way. And then put the arrow over the top, meaning it is a vector, and it means that every element in that vector is a 0. Okay? Now, they happen to tell us, surprisingly, that this 0 vector, and like I said, of the appropriate size, this happens to say it's only a 2 by 1. But both of the elements in it are 0. Okay? Now, what we're going to do here is write these elements here in here and go to town with it. Okay? That's going to be 1 minus 2, 1, 2, 3, negative 2. Make that times x1, x2, x3, and that is equal to 0, 0. Let's see if that is even possible to do. Well, let's do our matrix. Well, let's see if the sizes are right. That's the surprising thing. Let's see if they are. This is a 2 by 3 matrix. Got it. This is a 3 by 1 vector or matrix. And sure enough, since these inner numbers are the same, we can wipe them out, and that gives us a 2 by 1. 2 by 1, and that's exactly what we have. So at least the sizes work. Okay? Now let's see if our computations work. This element here can be represented by this one element here, first row by first column. That would be x sub 1 minus 2x sub 2 plus x sub 3 is equal to 0. Goodness gracious, I can't get that to draw well. There it goes. Man, I have seldom felt lousier than this. I've now drunk everything I can possibly drink here, and it's still not helping. I hate to do this again, but I'm going to eat another thing. I don't know why. Okay. That's this entry. This entry will be the 2-1 entry, second row here, first column there. That would be, yuck, 2x sub 1 plus 3x sub 2 minus 2x sub 3 equal 0. Okay, so now we've taken this matrix A times this column vector x and set it equal to this column vector 0. We've done it here the way it said to do it and written it out here, and then we did the matrix multiplication and get these two systems of equations. Okay, now we have to solve those, and I'm trying to get my pen to show. There it is. Okay. Okay. That was irritatingly problematic. All right. Now this is a bit bizarre. What we're going to turn around and do here is put it in augmented matrix form. Okay. So this is bizarre, but we're going to doing it because they told us to. That will be a 1 minus 2, 1, 0, 2, 3, negative 2, 0. It makes you wonder why we didn't just put this to that and we'd have it. Okay. Now, row reduce it. We want a 1 here. We got it. We want to make this become a 0. So how do we do that? Minus 2 times row 1 plus row 2. So we're leaving row 1 alone. 1 minus 2, 1, 0. Negative 2 times 1 is negative 2 plus 2. That, sure enough, gives us a 0. Negative 2 times negative 2 is 4, plus 3 is 7. Boo hiss. Negative 2 times 1 is negative 2, minus 2 is minus 4. And guess what? Negative 2 times 0 is 0, plus 0 is 0. So that stays a 0. All right, now the bad news is we need this to be a 1 here, and I hope I've done it right. Yes, I have. I think. How to get this 7 to become a 1 is to divide everything in the third row by 7. So I'm going to do it right here. Divided by 7, divided by 7, divided by 7, and divided by 7. Okay, so I'm going to write down that new matrix up here, and this will be a 1, negative 2, 1, 0, and this will be a 0, because 0 divided by 7 is still 0. 7 divided by 7 is 1. We wanted that to happen. Negative 4 divided by 0 is negative 4/7. I mean, not by 7. Goodness gracious, I can't even talk. Negative 4/7. And 0 divided by 7 is 0. All right. Now, the one last thing we need is that we got a 1 here, 0 there. First non-zero entry is 1 here. We need that to become a 0. So how do we do that? 2 times row 2 plus row 1. That should do it for us. Now that we have the leading one in the second row. And if we do that, I need more room to write. So let me come up here and see if I can come here. All right, we're using the second row, which is 0, 1, negative 4/7, 0. We're operating on the first one. Negative 2 times 0 is 0 plus 1 is 1. We wanted that to stay the same. 2 times 1 is 2. Minus 2 would be 0. And 2 times negative 4/7 would be negative 8/7 plus 7/7 will be a negative 1/7. And then that stays a 0. Okay. Now, let's see how we've done so far. Yeah. That gives us the matrix they got. Gauss-Jordan elimination gave that to us. What does this mean? Well, that first row says, well, let's start with the bottom row. X sub 2, that's what the second column is X sub 2. So X sub 2, now, minus 4/7 X sub 3. Well, X sub 3 doesn't have a leading 1, so let's let X sub 3 equal your favorite parameter. The book's favorite is always T, I think. Not always, but most of the time. So the second row here will say X sub 2 minus T, no, I'm sorry, minus 4/7 T is equal to 0, which of course makes X sub 2 equal to 4/7 T. And X sub 1 plus, no, I think that's a minus there too, minus 1/7 T is equal to 0, which means X sub 1, goodness, I can't get this to go away. X sub 1 is equal to 1/7 T. Now, that's one way to express it. But a simpler way was multiply each one of those by 7, and then you get, and that's legal as long as you did all 3 of them. And I can't seem to get my pen to show up. There it is. That then would be the ordered triplet T. Now my internet is going unstable, so I'll wait until it comes back. Okay. Did I break up a little there? T, 4T, 7T. Now let's just take a few points and make sure that makes sense. Of course, if T is equal to 0, that 0, 0, 0, 0, 0, 0 makes that work. When x1 is equal to 0, x2 is equal to 0, x3 equals 0, multiply those in, sure, you get the 0 product. Let's do one with just T equal 1, okay? And let's do it this way. 1 times 1 is 1, minus 2 times 4 is minus 8, so that would be minus 7, plus 1 times 7 is 7, that's going to be 0. Let's do the second one. This is T equal 1, so that would be 2 minus plus 12, it would be 14, minus 14, that's 0 also. That works. Let's get one more just for fun. How about negative 1? So this would be, if that's a negative 1, yeah, where is it? Right there. Negative 1, negative 4, negative 7. So that would be -1 plus 8 minus 7, sure enough that's 0, and -2 minus 3, no, minus 12 would be -14 plus 14. Yep, that works. Any t that you put in there is going to make that work. So there's our solution. X equal t, x1 equal t, x2 equal 4t, 4t, and x3 equals 7t. Now, here, goodness, I've run out of room. Let me erase some stuff. Let me figure out what I can erase. I need to get my pen to show up somewhere here. There it is. Okay. All right. Now, I think I'll erase this line down here. We've used it. We got it. We know what it is. I'll basically erase everything except our final solution. Goodness gracious, I'm running out of steam. It must be a Thursday. Okay, we're getting close to it now. Okay, let's go back to the draw mode. Okay, well, I got 2 minutes. Let's see if we can do it. This is what we wound up with. Maybe I erased too much. It was 1 minus 2, 1, 2, 3, minus 2, and then our x1, x2, x3 we're going to write in as t, 4t, 7t is equal to 0, 0. Okay, that's what we came up with, and we just sort of verified it. Well, here's another way you can write this. You could write this as 1, -2, 1, 2, 3, -2. But then this matrix here, this column vector here, we could pull the t out and have that times 1, 4, 7. And that's equal to 0, 0. Now that sort of looks odd because that t is sort of sitting in the middle there. But just pick a t, any t. Let me put this in parentheses here and multiply it by that, and you'll get that. And that's what I did when I picked just a few representative ones. And as I said, some of those were 1, 4, 7, 0, 0, 0, -1, -4, -7, 2, 8, 14. Any t that you choose, multiply it by all three of those, and you got solutions. All right. Now, what we almost were doing there was partitioning a matrix, but I think we just have run out of time, so we'll start next time, next Tuesday, top of page 46, partitioned matrices. Let's see how many homework problems we can do on this. Let me get my marking piece of paper in place here. We're almost through with 2-1, thank goodness. Okay, do either on page 48 and following, either 1 or 3, they're both at Calc Chat. Do any of the odds 5 through 9. Do either 11 or 13, they're both at Calc Chat. All these odds are at Calc Chat. Do any of the odds 15 through 27, there's a whole passel of those. I think you can do any of the odds 29 to 35. and I think you can probably now do 37. And I think you can go to any of the odds 39 through 47. And we'll hold off on the rest of those until we do the last couple of pages, and then we'll be able to do them all. All right, any questions? I'm so sorry I was feeling so rotten today, and it showed probably on how slow I was working, but goodness gracious, I'm just barely hanging in there. Any questions? All right, folks, as I say every time, please don't let your guard down. The virus is still there. It is a miserable thing. I think I've told y'all before several times, we know some people who have it now. Not pleasant. Some people are getting by without being too sick, but others are getting really, really ill. So don't play around with it. Have a good, safe weekend. Of course, working on linear algebra will make it a great weekend. But all of you can work on Cal 3 and differential equations as well, and it'll be even a greater weekend. I just ended the meeting. I didn't mean to. All right, take care.